Hello and good morning, everybody. How are we doing today? This is Jeremiah, and we are having another webinar. Irrigation one, of course. I hope that's what you signed up for, because that's what you're in for. I have a couple quick housekeeping items here. At the top of your screen, you might notice a little view options little thing there. You can click that to exit full screen mode, just in case you need to get to something else on your computer. Just knowing where that is handy. And it's also nice to know about that Q&A button at the bottom. I actually recommend go ahead and click it right now and get it situated, because it's nice to have that up on the screen so it's a little faster for you to type a question. But notice you're going to be able to see any answers that we type to other questions. So it makes a fun companion to this webinar, because we want that interaction. We definitely want a lot of questions. We've got some time reserved to address any questions. And we are recording this, so if you miss any part of it, or also just think it's so amazing you want to watch it again when you can't sleep, then it'll be here and ready for you. But yeah, we are going to be talking about pressure and flow. And now that I see that, I realize, there is one other important aspect, which is velocity. But we're going to get into that too. But the real basics of irrigation, but not that this is only a basics. I'm saying pressure and flow are the basic elements of irrigation. We're going to go into some pretty cool stuff, give you really good understanding of things. This is for someone of really any skill or experience level. We're really going to cover everything from fundamentals on up to some pretty good stuff. So I think I have exhausted my yibber yabber time. So I'm going to get this handed over to Jake, and he's going to take us away.
All right, thanks, Jer. Yeah, like Jer said, we are going to be taking a closer look at the pressure and flow as a whole, really taking a step back at some of this basic level stuff. So as it pertains to, things or things to consider as you start your design, definitely going to be a refresher for a lot of you. But as it was for me, it was good to kind of go back to the basics as it pertains to how pressure and flow really work. And like Joe said, the velocity does play a huge part into all of this as well. So hopefully takeaways from this webinar can actually be applied to not only troubleshooting things that come up in your designs while you use land effects, but just being able to make adjustments and have that ability to adjust the equipment that you do use on your projects to optimize what you have to work with. So I guess that's my little spiel at the first, but this is me. I am the irrigation specialist, and I've been doing irrigation for, I think, a little over 20 years now, which is a little bit scary. So our outline is obviously going into what we know about pressure and flow, anything and everything about that. We're going to touch on quite a few little things, and I do want to kind of state that this isn't going to be the be all end all, and I am not a physicist or a hydrologist for these types of things. So, we're absolutely open to the chat and open to the Q&As and hearing your guys' thoughts on things as well. So, but just really going through what impacts that pressure and flow. And then, of course, getting into land effects, just becoming more familiar with those dialogues, where to see the data, how to read it, and how to manipulate it. So just wanted to start out with this simple question is why do we even care? And why do we need to understand about pressure and flow? And not going into it very much, but just seeing some of the results. And I know that there are a lot of other factors that could play into things like this, but from a general level, these are the kind of things that we need to be aware of. Too fast a water, too large of zones exceeding the what we have available, those kind of things absolutely play into this end result. So this is what we're trying to avoid. Um, Jumping right into pressure, just the differences, the terms that we're going to be using, obviously, again, as a refresher, static versus dynamic. What is used as an available pressure and what we use as our working or dynamic pressure. So just understanding that static is literally not on and dynamic is when the water is on. So we're going to get into sort of an overview of what equipment has to do with this. This is this is my dad joke for the day, but this is Tina Turner's less known song right here. But talking about the main components of the design, if we're looking at this at a very simplistic level, we have our point of connection, our water meter, the stub that we're using, the well, you name it, the actual starting point of the design. And the POC is what we're considering to be our available from flow and for our pressure. And then if we go all the way down to the very furthest end of the design, this is our demand. And the demand really is based on the emission types that we're going to be using and sort of looking at it from not only a flow perspective, because that pertains to the zone and that kind of stuff, but the operating pressure of what we need this equipment to do. And there's where we're going to talk about, there's a lot of in-between stuff as well. And so if we look at that furthest point and we start working our way back, we have our lateral lines that connect into our valve. And so this is our zone. And then we have additional equipment, the backflow or pressure regulating, the RPZ, that kind of stuff is sort of what I'm showing here, but it could be any other amounts of equipment that like feed that main line. And what we're going to consider this middle stuff is the kind of the in-between stuff that we also need to account for, and really what gets affected as it comes back to cross-checking what we have available at the POC. So it's not just a simple, I'm running my heads at 30 PSI, I have 14 GPM, does that cross-check with what I have available at the point of connection? There's a lot of other in-between stuff, and that's the additional information and stuff that we need to understand to get a true number of what we have as a demand is concerned. So there's a lot of different methods to capturing this, and source data is obviously very, very important to us. Sometimes it's given to us by the city or by the engineer on site or whatever it is, but there's definitely other ways to capture that. So whether or not you're going to be adding on to an existing zone and you need to see what their current pressures are, and the flows and stuff like that, there's a lot of tools, a lot of ways to get that information if it's not provided to you. So just as a little snapshot and example of things to use for capturing that actual source data that we need to use. So where do we actually check this stuff, and why is that important to us, and what's important to check? So static versus dynamic, obviously we're going to be getting a lot of different readings, and so what numbers are we using for what pieces of information in when it is concerned for the actual design. So dynamic is obviously something that we're checking and is the most important from an operating perspective of what that system's going to be functioning as. And static is what we're going to have as that available pressure. And there's different places to check the pressure. So obviously having the right tools and the right hookups to the different positions in the line is going to give you different readings as well. The static picture, for example, we know from a dynamic reading standpoint, if we're reading on the inlet side of that piece of equipment, that we're going to have a different reading as if we were to check on the other side of that, because there's a lot of different losses. And as we start to talk about this, it's sort of clustering all of this information together a little bit. But this is where flow comes into play. This is where the velocity comes into play. This is where the equipment comes into play, and making all of that kind of make sense. So the fact that we have a X amount of flow going through that device, and if we check that on the outlet side, we're going to definitely get a different reading based on the amount of pressure loss going through those pieces of equipment. So it's very, very important to understand and take multiple readings from different places so you understand what your site's doing. Not only just that, but it's really where it lands in the site. You know, elevation plays, all things considered, a huge role for how the system's going to operate. So are your valves up high and your head's down low, or vice versa? Is your point of connection somewhere different than where all of your design is going to be? So we need to understand and know where to check all of that information, because not only is it a and this really pertains to, from an elevation perspective, pertains to a static reading, because while it also does for dynamic, the dynamic part then takes into consideration the friction loss on top of that. So just as a snapshot there, want to try to move fairly quickly into what we have next. So why don't we get right over to talking about pressure and flow. So before we get started fully into analyzing all the pressures and flows and how that all operates, I wanted just to do a recap of where this data is stored and how it's stored and what affects what position of things. And what I mean by that is we have our irrigation preferences, and the irrigation preferences is, again, that place that holds the standards for how your irrigation stuff works, really for any of your land effects items, but particularly for this, how is this information set up? So obviously our flow and pressure units is a really important thing to understand. So if we're working on maybe international projects or just right here in the States, what is that flow and pressure unit set up to be? So making sure that that matches appropriately for the preference set that you have as you start a project. The only other part that we're going to really focus on past being able to set your pipe classes, because again, as we start to factor in what our velocities are, what our friction losses are going to be, the smoothness of the pipes and that pipe coefficient is going to be pretty important. So having that proper data and the right pipe sizes and stuff like that can all be handled here. But past this is pipe data, the pipe data defaults. Now, I'm bringing this one up mainly because we have a lot of people that, you know, might be trying to alter their design and what the system is producing size-wise for the pipes, and they make changes here and it doesn't reflect in their project, in their design that they're working on. And that's because this is more of a static set pipe data look for when you start a new project. When you start a new project, this information gets copied over and is put into the pipe data in your actual equipment irrigation manager. So as long as your pipe data defaults are set how you want them, and you remove different sizes that you want, you understand what class you are using, the different class amounts that you might be using for your laterals and for your mainline. And then, of course, setting sort of the default. This is where it pulls this when you start sizing your pipes. So really making sure that this all is dialed into how you typically want the system to look at stuff is the most important part in that preference set. So once we have all of that set, that is really ready for us to start a new project as we go into, our project list, say new, and we use that preference set, it's going to pull in that information specifically to our irrigation manager. So once it's here, we now have a couple different options. So going into our pipe data, just because we're there, it's going to look all the same, but you can modify this project by project if something's very unique. Maybe you can't use a certain size, or you don't want to use a certain size, or it requires a certain class of pipe. You can change it here without affecting your overall amounts. So really dialing this stuff in on a project level is again pretty important there. Our next little bit of information is our source data. So this is something that if you're given that information, it's great. You can put it in here. We have 3 different ways to actually input a point of connection, and obviously you can have several different point of connections if that site deems necessary. But again, this is about analyzing the site, understanding what it is that you have to work with. So if you're working from a well, this is a great way to use that custom max available, understanding what the pump's going to produce, or the well's going to produce for you, the tank's going to produce for you. And then if there's just absolutely no PSI available and you want to introduce a pump instead, that's great. Or you can just simply put the flows and the pressures here, just like that. Point of connection size, again, is more of one of those existing tapping into for a future position. So being able to grab a size of pipe and have it give you at least the flow available there, and then be able to give you your pressure. But obviously the most common one is the water meter that you're provided, something that's stubbed into your lot, and you're going to be sort of tapping into that guy. So understanding that not only does my water meter size affect the flows that I have, but I also have, again, some standardized numbers here that this really matches the back of the book numbers from a water meter size and what they have to offer. But you can see that I can start to adjust and utilize more of a safe flow number than what that size of meter can actually do at full-fledged. So this is pretty standard there. But then again, we give you a little bit more information regarding the service line side of things. So what size that service line is there any elevation change through that service line, and what that length is basically from that, call it the roadway, stubbed into that water meter. What is the length of those items? And then the class, because all of this information is going to give us that additional middle information for anything left over. So say you needed, it was a little bit of an elevation change of where they dropped the water meter. Being able to account for those little bits of pressure could make the difference in your actual design. So being able to account for all of that right here, the system will then take that and use it as it's doing its calculations. But obviously, if we're going to go ahead and say this is just simply a 1-inch meter, maybe it was a 2-inch line, and this is good enough for me. You can see what I have available for a flow standpoint. So right off the bat, I start getting this sense of how I'm going to be starting to zone things out. I can't put any zones that are bigger than that 37 GPM. So really good kind of sense before I even get started of what we're going to be doing here. So we're not doing a lot of rework trying to split zones up and all that kind of jazz. So static water pressure, again, if we're taking that reading ourselves and we understand what it is, we'll go ahead and throw in, let's just say it was 55 PSI. Now you'll notice that the available isn't that full 55. It's because what we're trying to do now, and understanding, sort of making those connect the dots a little bit, if you will, is it's taking the flow that we got going on, through that size water meter and taking the water meter loss for it. So it's already accounting for, again, that extra loss through the equipment, specifically that pertains to this right here. So giving us a better snapshot of what it is that we're trying to achieve. So once we have our water source information set up, and again, if you didn't know this, we can leave this all blank. And I am going to just go ahead and leave this blank for now, just so that we can see what it's basically doing here. We'll go ahead and say okay to that. Now, when it comes to, again, now understanding the site, what equipment that you need to use, all of that kind of good stuff, we are going to go through the same process, and I'm not going to really belabor this too much, but we'll go ahead and we'll add something for now. And we'll just go ahead and grab a bubbler here, and we'll add it to the project. And we're brought to this. So any kind of emission device that we're adding to the project, we need to understand what its operating pressure is, what that dynamic pressure is. We call it the design pressure. So we need to understand what we want it to be run at, because that's going to automatically start dictating what it is that we have set for our actual design. So for this example specifically, I did throw in a rotor already, and you can see that he's set at a design pressure of 50. And the nozzle itself obviously is looking at that performance data, and it's given me my flow for that. So if we're going to kind of go back to that picture that we sort of initially first saw, this is what we've kind of set up, just as a very simplistic version, obviously. But we need to now be able to size this. So if we're doing that Hazen-Williams old school by hand, we're always thinking about this from the furthest head and working our way back, and obviously counting, using the charts in the back of the book for our flow and the velocity, and therefore our friction loss. So this is where all of these numbers, the flow and the pressure, all of that kind of stuff starts kicking into play. And we're looking at this thinking, okay, what is my flow here? And I got 13.8. So I would be looking at the back of the book, finding that closest to 13, maybe 14 GPM, and doing the calculations from a friction loss standpoint. Now, this is where velocity comes into play. So we'll go ahead and size this so that we can start playing with this automatically. I like clicking on the valve callout to size because it's a bigger target. But we're brought to this guy. So this is our size lateral dialog box. And what I want to obviously hope from achieving today is a better appreciation for what the system's doing for us now. So we're going to be able to do a lot of playing without doing a lot of math for this example. So we'll go ahead and just sort of walk through all of these different things. Our design pressure, we know we had at 50. Our velocity, again, we can start to play with this and see what exactly I want. So this is one of those garbage in, garbage out scenarios where if I'm not setting an appropriate number, the system's just simply doing the equations. This is just physics. It's doing the calculation that you'd be doing by hand, but a lot faster. So if we don't give it the right information, it's going to give us a bad set of data. So if we're looking at this, our maximum velocity that we're looking for is 5 feet per second. That's great. Our actual velocity, and this is something that I'll show you just here in a bit. It's kind of a back and forth thing here, but I'll show you what this entails in just a second. The pressure variation is really what we want to allow the system to lose through this this sizing equation here. So if I'm taking this design pressure, this pressure variation is a percentage of this overall design pressure. So you can see that if I dropped it down to 10, it's going to match 10% of what that design pressure is. So I need to be comfortable with the way that I design, and maybe I have some rules of thumb that I don't want to exceed more than a couple pounds of loss. So maybe it is that I only want up to 150, 1.5 psi loss. Now, if I decide that I want to change my velocity, this obviously has an impact on what that friction loss is going to be. So the rule of thumb here, if we're going to try to relate these two things, is the flow has a direct correlation with the velocity. So the higher the velocity, the lower the pressure, meaning the higher the velocity, the greater the friction loss is going to be based on that flow. Because generally speaking, if you're moving the velocity faster, there's going to be more flow. And so if I'm going to slow the water down, that means I'm going to have lower flow or lower pressure, because that velocity creates turbulence in the pipe, and that turbulence creates that friction loss. And so if we're trying to squeeze a certain amount of flow into a pipe at a certain speed, and we're still speeding it up and we're still trying to fit it into that pipe, there's going to be a higher and higher friction loss, which means our pressure is going to drop. So this is the part, the magical part of this math stuff that just, if you start to think about it too much, it doesn't make sense. So I try to move along a little bit quicker, but I just want you to see that correlation, because watch what happens if I speed up my water. What should happen to my pipe size? So we can see this before doing any calculations. We can see what that 13.8 GPM is needing based on the speed of water and obviously the friction loss that it's providing. So if I speed up the water, what should happen to my pipe size? And obviously nobody can answer. Maybe you're answering in your head right now, but the pipe size is actually going to go smaller if I speed up the water. But what's going to happen to my friction loss? The friction loss is going to go way up. So we can go ahead and start speeding this up, and you can see that just based on our setting here, and we'll change this in a second, but I wanted to show you the fact that the system is actually cross-checking you, saying you have set in place a limitation for me, and that was not to exceed 1.5 psi in friction loss. And you can see that if you exceed 5.2 feet per second, it is going to exceed that. So I'm not going to go any higher than 5.2. But you can see that if I start sliding this up, you can see how much I'm allowed to lose. So you can see that, and obviously at the given point of the flow that we have, it does stop at what it needs to run. So there is a fine line of playing with this to get accurate numbers, but this is just the great example of being able to find what that is. 5 psi, I need to be at least at 5.2 feet per second before it allows me to only lose that much. So it's very, very cool to be able to see that. I can turn this off if I want to just ignore any limitations and just let it be what it is. But you can start to see that I can get certain sizes based on how fast I move the water. So that is actually, I think, beaten enough, but we're going to move sort of down this now. So now that we understand how fast we can move the water, we have a couple different other things just to account for some other minor stuff. So we have our fittings factor, which does play a very small role in pressure, but just to account for any of that stuff as a buffer. But then we have elevation loss, which we'll handle in more of a complicated example in a little bit. But then again, loss through the valve. And the loss through the valve now has everything to do with flow. So it's a pressure loss based on what the valve itself can handle going through it. So just like we sort of did here with that speed of water and the amount of flow, the valve has a certain amount of flow that it can feed while producing some type of friction loss through that valve itself, pressure loss through the valve. So we can now make the determination, does it make sense to keep a 1-inch valve, or does it make sense to up it and only lose, basically cut that loss in half? So understanding the equipment that you need is absolutely imperative as you're starting to do these designs, and really check and make sure that you're using the right equipment for, this scenario. So what's acceptable to you from a client perspective, cost perspective, to then obviously what's going to work for the design. So once we have all that stuff figured out, we can just simply say, okay, and the system's going to basically size back down to that valve, and it's going to label our pipe, obviously, but we can now look at this information. The information that we have in this given piece of pipe says that it's got this 13.8 GPM, and the pressure in that pipe is actually 51.36. So not only is it taking the design pressure, but it's actually taking that friction loss of that length of pipe and applying it to that demand as well. So we're now starting to account for all of the demands clear up into this valve. So now what we got obviously is now working our way back through from the valve to the main line. So we need to size that main line and basically see how this cross-checks with or compares with what we have available. So we obviously have one valve, so that's what I'm going to do. But a very similar kind of theory is behind this, is when sizing, is velocity. And this is all that we need to understand from a mainline perspective, is how fast do we want that water to move. And you can see as a pre-calculated anticipated size, if you had a looped versus standard, what it would be doing. So maybe it is that you wanted to try to keep with a 1-inch pipe size. You can start to see what effect that is going to do. So obviously the general rule of thumb is 5 feet per second. So we'll go ahead and just say okay. Now, this is okay because I haven't sized that one, but the system's now going to cross-check what I have available and what I have as a design demand. So if we're going to look through this real quick, because we'll analyze this later as well, but it's grouped into different things. We've got basically our overall snapshot of what we have available, any elevation changes and stuff like that. So what our total pressure available is, and you remember we left that 0 on purpose. But then our max station flow versus what we have available here. So we need to understand that when it comes to a critical analysis, it's actually the pressure that we're most concerned about here. Obviously, we need to understand that we're not exceeding our flows as well. But from a pressure standpoint, we need to be able to supply what those heads are going to do, because they might not operate. And again, the pressure changes not only from equipment, and I'm going to be saying this quite a few times, so forgive me, but not only from the equipment, but it's based on the flow and the speed of water. That really affects what that pressure ends up being, because if you put too many heads on a zone, you max out that flow, the velocity technically increases with the increase of that flow, which is going to drop your pressure based on that additional friction loss. So we really want to understand what that critical station is, not only to make sure that we're good from what we have available, but what our pressure demand is for that specific zone. So we can read through this and we can see that this is that required pressure at that station. So that's the demand, that's the pressure, design pressure, that's the loss through the fittings and through the pipe and through the valve. So that stops there. And then we have the additional loss going through the main line and fittings. Any elevation that we might have different from the valves to the POC. And then we come into our other key pieces of information, which is the backflow. If you don't put the backflow in, it's not going to put this into the analysis here. But that is a very, very high loss for a piece of equipment. So when you're running a low pressured available system and you're trying to stay with low pressures, there are going to be limitations, some things that you just simply can't change, which means that if you're exceeding because of some of the equipment, and granted, this is a pretty standard, anywhere from 6 to 12 pounds of loss is pretty common. Sometimes 4 you can get away with, but depending on the flows that are going through it and the size that you put in, you're just locked into what it is. And I really take this irrigation design as a whole as your design is your design. So if you've done your homework, you've done the right equipment, you're watering to the site based on what it needs, understanding, it's watering days and all that kind of jazz. If it's still exceeding what you have at the demand, or sorry, at the source, then we need to figure out how to supplement that stuff. So introduction to pumps and other splitting of zones or trying to do that is what you really need to look at. But leaving the pressure at 0 allows us to see what our design pressures are required. And this is sort of a good snapshot, especially if you're just trying to get a sense of everything and you kind of don't care quite yet of what the service is, or you're waiting for it to be put in and tested. This is a really good snapshot to be able to tell the client, say, look, this design is based on this pressure and on this flow, without needing to say, no, it won't work. It's basically, this will work at this specific pressure and flow. So we're going to just say okay to that. And we're going to move on to this other little example. It's obviously important to trust but verify, and we fully support that. And the way that you can actually do that, especially if you're playing around and you're really not trusting some of the numbers and stuff like that, it really comes down to being able to play with, testing it from an apples to apples perspective, and being able to not only use this as a testing point, but use it in real world design stuff is actually pretty cool. And those of you who are not using the caps yet should definitely check them out because they're really cool. But in auxiliary equipment, there is a cap section for a system monitor and for a specific cap. And what they do is they basically help without placing, your whole design and stuff like that. You can fill out a specific demand and pipe to it, and the system will calculate based on that demand. So for this example, I wanted to be able to kind of cross-check and see how things relate to even the book, because again, the system itself is doing a little bit more tweaking and analyzing based on total flows versus lengths versus the speed and stuff like that, to where you might not see, or you might read the book and see that it should be a certain size when it's not sizing it that way. Well, this is a great way to cross-check what it's actually doing. So we're going to just simply size this lateral pipe based on 12 gallons a minute. And if I look at my book, and I'm using Schedule 40, and you're welcome to pull out your pipe charts in the back of the book to follow along. But basically, looking at a 12 GPM, understanding what kind of losses and velocities I should be looking at um, is really what we're kind of looking at here. So if I were to sort of start sliding this around, you can see that at 5 feet per second, it really says that I can get away with 1 inch. So I look in the book, I see there's really not a 5 feet per second line. It's actually 4.62 feet per second, but the friction loss based on that is actually 3.69. So right off the bat with that number, and if I go to 4.6, there we go, or 4.5, you can see that that's where it starts jumping to the next size available. So increasing or decreasing that velocity, there's only one way to keep that friction loss down. It's either changing the size of pipe or lowering the amount of flow. So we're keeping the flow there. There's a lot of different moving parts in that, but it's lining right up with the fact that I can increase or decrease based on that, or again, speed up the water and then start following the chart down and seeing the different sizes that way. So I'm going to stop right there. Are there any questions, or a reminder to people, start getting your questions in as we move to the next example, Jer?
We had, a couple simple little questions. I think I was able to answer. So definitely want to remind people, there's the Q&A box, and if like kind of further clarification on those topics. Otherwise, we'll kind of revisit those and any other questions that come in when you're done.
All righty. Okay. Well, so we're really going to move on to kind of a full design at this point, and it might seem pretty repetitive, and we are going to be, repeating some of the size stuff, but just really hitting home how the system is really functioning this, and what to look for when it goes. So there definitely might be times where you have different regulations or required to maybe limit yourself to using certain pipe sizes, and maybe different loops have different sizes on them and stuff like that. We're not going to get into the what ifs on existing irrigation and how to match those per se. We'll definitely be probably mocking up another webinar for that. But what's important to know is that we have full control from what the system sees as an available pipe size, because we might be kind of in the mindset that I don't use 1.25 inches. I only use 1 inch and 1.5 inches. So where that line is drawn and being able to shift those sizes appropriately for what it's used is going to be sort of important there. But again, letting the system, and I'm kind of in the mindset of letting the system have full range of available options, because a lot of times, people go, I only use 1.5 inches, that's it. But then they start getting into the system's stopping me from using it. It says that I don't have a big enough pipe size. It's again straight math to the fact that their demand, what's in the system, what it's trying to calculate based on the velocity and the flow that they got going on, will not fit through that 1.5 inch pipe. And you might say, well, it works out in the field. Well, it might, but what it's actually doing is it's actually on that far side of the preferred way that it should be watering. So whether it's really using too much, or it's actually sped up a lot faster than you think it is, and so you're getting a water hammer, and and you name it. There's definitely something in the design that isn't fully jiving, where it's maybe misleading. But here's where you have full control of what that is for what we size. So we'll go ahead and size these pipes, and I can click. Again, clicking one valve at a time really lets you analyze how each zone is going to be run. This one's pretty nice because it's all consistent. So I can see this is what it's going to do here. But I'm going to go ahead and just assume everything's kind of good there. And I can see, wowzers, you can see that if I were to jump to a 1-inch pipe, that loss is quite high based on this total flow. So we'll go ahead and say okay to that. And we're good. And you can see here too, I don't have minimum pipes labeled there, but you can see that this is where the transition was. So if we were to look at any part of this, this is where you have these tools kind of available to you from a analyze standpoint to see what kind of losses are coming out of that specific part. So the further we move closer to the end, the less additional friction loss is happening, of course, but it's accounting for all of that there. Now, if we were to click on the valve or valve call out, we can actually see then that station analysis, really what it's doing here. So we can start to analyze and see, does all of this make sense? You know, is this what I anticipated it being? If so, great. And that's right there in the analysis button. But I'm going to take a little step back. Actually, we'll go ahead and move forward a little bit, and then if I have time, I'll take a step back on some additional tools that help zone things out and show that kind of flow stuff as you are doing the design. So we'll go ahead and do our fancy size all. And again, being able to adjust the key pieces, the velocity, what that variation is across the board for all zones. Because sometimes you might want a different zone to be run at a different deal. You might want it sized differently. So that's all here. But if you want it uniform, being able to do that, literally go through all of the valves at one time and size everything for us. And we're going to size the main line here. Now the main line has, especially from a larger perspective and integrating loops and sub loops and all that stuff, definitely gets very, very complicated and very tricky to kind of unravel and confirm everything's good. But from an overall perspective, looking at single valve versus multiple valves at a time, especially integrating with loops, the multiple valve operating at a time gives you some pretty good control from like if I want everything to be a certain size. Now again, we can always shift the pipes sizes available that the mainline has to use so that it just uses that size. But if it's in need of anything larger, you might get in trouble there. So we'll go ahead, just for fun, we'll go ahead and do single valve at a time. And we get something like this might come up. Now, pressure available at the POC has been exceeded. So what it's going to try to do, again, now that we have this understanding of the fact that if we slow the velocity down, our pressure losses will also go down, we might be able to get by with it. So let's go ahead and let the system try. It's going to try. Now, it stops at 3 feet per second. This is sort of our cap, sort of that fine line of how slow do you slow the water down before it's actually not moving. And 3 feet per second seems to be pretty fair, pretty standard. So it did max out at that point, and it says that we can't size the main line. So it does have pressure flow requirements that exceed that. So I would say for those who are new to this and coming into this, say yes to see that more information. But we already know what we're kind of looking for now. And now I can start to glance at this and see, is it my flow? Nope, I got plenty of flow there. Definitely looks like it's this one of these stations. And we can start to analyze what might be going on here. Looks like I got 7 pounds of loss through the main line. Again, one of the factors from a velocity or a pressure loss standpoint, friction loss standpoint, is the length of pipe. So we might be trying to take a lot of water and bringing it a really long way. So the longer the pipe segments, the higher the friction loss is going to start being. So that to me seems actually acceptable. And we're going to come through, and it just looks like from what I have available is just simply not enough. And I can tell that right off the bat because I'm using heads that require 50 psi. So if I've got a piece of equipment that requires something that's almost already to what I have available, I know it's probably not going to work, especially accounting for all of those other losses through back to that available point of connection. So we're going to say, okay, now I got to figure out what to do. Is everything right? Do I just need to add a booster pump? Or maybe I took a wrong reading? Those are the things that we need to figure out. So we'll go ahead and say, oh, it turns out that the guy measured the wrong something, or he was just guessing. And so let's just say we had 75. I'm giving some very nice examples that probably rarely ever happen. So you do need to make that that decision. So we're going to go ahead and size. We'll go ahead and say okay. It looks like it's running into it again, but look at what it did. It only stopped at 5.6. So it determined that it was able to slow that water down. Oh, and I guess I had it a little bit higher than the 5 feet per second right from the beginning. So maybe my rule for this large site was 6 feet. So you can now see that obviously the flows are what the flows are, but we have now a little bit more loss. It found a different critical station, by the way. It went through and analyzed a little bit more, found this guy to be the critical station, but it shows me now what I have left. And this is a great number to kind of maybe have under your belt from a either best practice or office rule of thumb that you guys want to always have anywhere from 5 to 10 psi left over for any kind of fluctuation or maybe breaks that happen or something like that you want to be able to account for without hurting the actual design. So if this all checks out for you, we can say okay, and we can kind of go through and we can look at what the system's doing here. So the loop is obviously taking and finding that worst case scenario path. So to think about that from that high level is we don't care about any valve that is under what that critical station is because we know that it will be accounted for. So this system is sized for that specific valve, that critical station. And we can see that it's splitting the flows. And we're not going to get into the technicalities of all of what it's analyzing, but it really comes down to path distance and percent distance around and splitting things. And that's for another day. But the system definitely is analyzing any and every path for what will work for that system. So once we have all that sized, we'll go ahead and drop in our valve schedule because I really feel like this is a great snapshot for the entire system when it comes to pressures, losses, and even then elevations. Let's just throw this guy in here. And you can see that now I have a snapshot of what my flows are, what my design pressures are per zone, and then the reflective friction losses through the actual lateral lines. So we obviously have different lengths of paths and stuff like that. But we also have then our valve loss, which is consistent because we're using the same valve. It's got the same flow. That makes sense. But then we have what's required at the valve itself. And then since we size the main line, it shows us what we actually need at the point of connection. So really, really great snapshot of everything. People can actually cross-check to make sure that, yes, this is the highest demand type of a thing, and kind of make sense of it that way. Past this, let's go ahead and really quickly account for elevation, because that might totally change things, right? So if you've gotten an elevation plan and there is elevation set to each one of those polylines, we've got a very, very cool tool, our spot elevation tool, that allows us to place a grid. And we're gonna be very loose with this right now just to speed up the process. But every 60 feet across this right here, this section, it's going to actually place a spot elevation on each one of those respective contours that it finds and fill out the appropriate elevation. Appropriate being what it finds that elevation to be. So if they enter that elevation in wrong, then we have a problem. But you can see that pretty easily in what I'm going to show you. So what's nice about that is it just placed all those for us very quickly. But for irrigation, we definitely want to be somewhat liberal with where we place them, because the system is going to start looking at the valve and where its closest spot elevation is. So you might need to place a couple other elevations into the plan that we're not going to worry about right now. But you might also then see the furthest head and make sure that it lines up with an appropriate elevation. So if that's actually okay, we're going to go ahead and size things one more time. Size lateral pipes. But now what you're going to see is this box is ungrayed, so we can check it if we want to. And we're going to go ahead and say okay. And it's going to size things, and it's going to take now, if I were to look at one guy here, you can see it takes into account then the elevation difference from valve to furthest head and puts that additional elevation loss in there for us. So that's what it did. We're going to go ahead and size the main line, and we're going to choose the same option. And we're going to say yes. Let's try to slow it down. Ooh, looks like we exceeded now. It worked before, it doesn't now, and we can try to figure out why. But what's kind of cool is you can now start to see that that is what it's accounting for. There's another 10 psi somewhere that I just didn't have. So if we go ahead and add a pump real quick. Turns out that I need a pump. I'm just going to do a generic for now, and an increase of, let's just say, 50 pounds. And the station flow, I can get 150 out of that guy. It's cool. I'm going to place him. And we're going to go ahead and resize this main line. Spot elevations. Give it a sec. And while we're doing this, Jer, are there any last questions?
We've had some really good questions here, and so it might be nice to get to some of them, but just Good questions on loops and on pressure loss. But why don't you continue your thought here, and we'll
Okay.
see what we can get to.
Well, we're right down here. So it now looks like it obviously passed because we had that supplement pressure in there. Um, but we're going to just run this schedule one more time, make sure all that's checked. And we can start to see valve to head elevations and the valve POC to valve elevations there. And you can then obviously see that the numbers reflect that now differently than what they did before. There's some higher ones in here. But a really good snapshot to be like, hey, why am I losing 100 pounds of pressure? And you see that there's a 300-foot elevation difference between one of the things. It's really easy to start to cross-check that kind of stuff. But that now gives us a way better accurate sense of what the systems are going to actually operate on based on the fact that we can simply integrate those in. So leave it there. Let's open it up for any questions you want to do.
Okay, we definitely had a great question on just on looped main lines. Just saying, well, isn't don't looped main lines typically have like half the friction loss? And I was saying, well, kind of depends, but because with a loop system, you have more pipe, and then a lot of times they do a looped main line to be smaller pipe sizes. So in fact, very commonly, a looped system can actually have more friction loss. And so it kind of depends, it's the main thing, but I would just tend to say that's the beauty of land effects is, try it, do a test case with some caps and do one looped versus not looped and compare the results. And that's the real beauty of it is you can really see how different situations cause different results.
Yeah,
And
throwing in shut-off valves in places just to turn it off and let it go one way versus the other way and really see what it's doing.
And let's see. Also got a question on, what happens with a drip system when you get to the critical analysis and suddenly you don't have enough pressure. And, I know the times I've seen it, it's almost always the loss through the drip valve kit. But, don't know if you want to talk any further on that.
Yeah, no, that's a pretty simple one. I mean, when we talked about it is what it is from a design perspective, I mean, that's the equipment you picked. That is the specifications that they hold, and those charts are tricky, but yeah, required inlet is always typically higher than the required outlet based on flows. So if your flow is on the high end of that chart, it's going to be creating a lot of losses based on what you have to have on that inlet side. So when that comes to fruition, it's easy enough to add a standard valve and call it a drip valve, but say it doesn't have a pressure regulator on it. Because if you're running at low pressures anyways, you're more than likely going to be adequate enough for it. But you can also put on a regulator filter add-on after the fact on a regular valve, and see if that does it for you too. But yeah, it's just sort of one of those, it is what it is.
I think we might need another webinar covering all those sort of drip issues would be nice,
Yeah.
definitely the thing. But, well, golly gosh, look at the time. What do you know? Another hour has slipped by. I hope you guys had a lot of fun and enjoyed this. You're welcome to reach back out with further questions, further ideas. We always need your ideas for future webinars because other times we just sit around going, what do you think of this? What do you think of that? So please feel free to always give us what you think would make a great webinar. And hope you enjoyed it. It's been recorded. It'll be on the website later today. Have a safe and fun weekend.
Thanks, guys.